Hello, my name is Indigo. I am a student at Florida Institute of Technology here in Melbourne, Florida. I work with Dr. Andrew Palmer in the Palmer Lab of Ecology. I am currently a senior here studying astrobiology with a minor in human factors, and I am about to walk you through a little bit about the project that I've been working on this past semester. So basically, all in all, I am testing radiation recovery and resistance in Anabaena cylindrica, which is a type of cyanobacteria or just a really, really old type of bacteria. In fact, so old it is one of the oldest living organisms that is capable of photosynthesis on the planet, which is really, really cool. And because of this, they're believed to have been responsible for the great oxidation event that caused our ozone layer. So they basically took our planet from not having no oxygen to being filled with oxygen for us and every other species to be able to survive. So, because they were here before the creation of the ozone layer, our ozone layer is responsible for keeping a couple types of detrimental radiation out, the most prominent of which being UVC radiation that is given out from the sun. So the sun gives out three types of radiation: ultraviolet A, ultraviolet B, and ultraviolet C. Ultraviolet A and B are highly energetic, so they're able to pass through the ozone layer, which is why we get sunburns if we're in the sun for too long. That's basically what you get it from. But UVC is very detrimental to humans and organisms alike because it can damage your DNA repair mechanisms. So it means if your DNA replicates, which is how your cells kind of rejuvenate themselves, then there could be a problem with that happening, and it can lead to all sorts of problems like cancer. So, in other places in the solar system, there are still heavy doses of UVC radiation because they don't have the kind of ozone layer to block it like Earth does. So, to create settlements on different planets, there needs to be better protection from this type of radiation. Cyanobacteria, as a pioneering species just basically means that it is capable of going in and kind of terraforming the planet to be how we want it to be without any prior things being added. So it's one of the first things that is able to terraform something to act as a biofertilizer, if you will. Um, because there are still other places in the solar system that do have these heavy doses of UV radiation, we need to use cyanobacteria, which can provide radiation protection, but it can also transform this regolith for plant growth. As I said, it can act as a biofertilizer. So the cyanobacteria that I'm looking at specifically is called Anabaena cylindrica. It is an aquatic cyanobacteria mainly used for fertilizing rice paddies in India and China. So I hypothesize that it will be able to withstand UVC radiation and thus may be able to support plant growth and regolith-based agriculture, where regolith is basically the dirt from other planets that has no nutrients. So on the bottom left, you're able to see a picture of my setup. This is basically just an illustration showing my plan. So I would grow up this cyanobacteria and then divide it into three groups where I would uh, expose it to UVC radiation for 15 minutes for the first group, for 30 minutes for the second group, and for an hour for the third group. And then I also had a control that would not get tested with radiation at all, just so I could have something to compare it with. After it was irradiated, then I would perform a chlorophyll extraction to see how much it's able to grow and recover. As I said before, cyanobacteria is one of the oldest photosynthesizing compounds or organisms in the world, so it has chlorophyll. And a good way to measure if something is not living anymore is to see how much chlorophyll it has. So that was basically the diagram of my project. And then in the middle of my poster, you can see the data that I collected. So I used plate one as a control group. And then as you can see in the graph also, that is just basically showing the amount of chlorophyll that was in before I UV radiated them and then after I UV radiated them. So you can see some negative numbers in the after irradiation section. This is after they have been exposed to UV radiation for different amounts of times. Um, but You can see some negative numbers and some positive numbers. This just shows the great variability that Anabaena cylindrica has, where if some parts of it will die out, there are still some parts of it that will stay strong. And then in the middle of my poster, you can see a picture of my overall setup for exposing these different bacterias to UVC radiation. So I borrowed a UVC lamp from Dr. Kelly Hunsucker's lab, who we work with here at Florida Tech, and I suspended it 12 centimeters above the plates in a hood that would protect me as well as the sample. And then the bottom picture on the middle kind of row just shows the growth throughout 1 week after irradiation. So the first set of plates, the first 3 plates on the left, show its pre treatment state. I have the 15 minutes at the top, the 30 minutes in the middle, and then at the bottom, the 1 hour. So you can see in the following pictures, over the course of 1 week, it was able to grow and recover, and then even start its recovery process. So that's very promising, and it just basically correlates the data that we have in the graph and the tables. So, in conclusion, after doing this experiment a couple times, I was able to prove that Anabaena cylindrica did show signs of recovery following irradiation, where it had its growth, which is shown on the plates, and the restoration of chlorophyll, which is shown through the data. This supports my hypothesis that Anabaena cylindrica has regenerative qualities for UVC radiation, which makes it a viable option for future space plant inoculation. In the future, I plan to perform this experiment again with the plates that have already been irradiated. This is just because I want to see if it has even more resistance. As you can see, the plates, the cyanobacteria grew back with a vengeance, and it grew back a lot darker and a lot thicker. So, this leads me to believe that it has some upgraded kind of ways to resist UVC radiation. So, I will be testing that in the future. And then I also want to mix it with a liquid culture to see if it has any qualities that would make it able to escape from the UVC radiation, and kind of sacrifice the top layer so that the bottom layer will have the living acylindrica on the bottom. And then I'm going to continue monitoring its biomat potential, which is just basically if it's able to form a kind of protective film over top of it so that the top layer is sacrificed, but the bottom layer, which is where the living organism is still viable. From these 2 points, I will be able to see if Anabaena cylindrica is a viable option for dealing with radiation. So, in our lab, we've proven in the past that if we take regolith or simulated regolith, for example, Martian Mojave simulant, and we kind of incorporate a cylindrica as a biofertilizer, we're actually able to grow up plants for a very, very long time. So I will basically be able to see if it is a viable option because it already has potential as a biofertilizer if it's able to protect our plants from space radiation. So, all in all, that is the basics of my project. And if you have any questions, feel free to email Sam and then she'll email me and I can get back to you about anything. So, thank you. Bye.